1 o'clock.
Okay.
Good afternoon, everyone. And this is William Liu, and I'm the chair of IEEE VTS New Zealand North chapter. And today is my great pleasure to invite, Professor Wyglinski, sorry, it's my English also is an issue, to offer us a talk about this connected vehicles. I hope you guys already read the bio of Professor, so I hope I just have a quick introduction here. Dr. Wyglinski is an international recognized expert in wireless communications and cognitive video, 5G, connected vehicles, and software-defined radios, and also dynamic spectral access, vehicle technologies, and wireless systems optimization and adaptation, and also the cyber physical systems. And he is a full professor of electrical and computer engineering and a full professor of robotics engineering at the Worcester Polytechnic Institute, US, as well as the director of the Wireless Innovation Laboratory. And Dr. Wyglinski is very active in the technology community. So probably most of you know, he is our previous president of VTS. So it's I really thankful, and he can offer us these talks. I don't want to become the master of today. So basically, I like to pass my time to Professor Wyglinski, sorry, to offer us the talk. And I got a little bit of thing. I try to sort it out. So after that, I hope Dr. Jingma Julia can help me to chair the discussions. Okay. Yep. So Tam, I pass to you, Alex. Yeah.
Thank you, William.
Yep.
And thank you all from all time zones and all parts of the world for attending this. And I'm really honored to be here. And again, thanks to William for his kind invitation. Like we've been exchanging emails, and I'm really happy that we were able to make this work in terms of having a talk on some of the work that I've been doing here at WPI, Worcester Polytechnic Institute in Massachusetts in the United States. So I'm going to turn off my video so we can conserve some bandwidth. In terms of what I do and stuff, and so first of all, my name's Alex Wyglinski, so please feel free to call me Alex. So I'm a professor here at Worcester Polytechnic Institute, and I also lead a research group called the Wireless Innovation Laboratory. In this invited talk, I will be presenting my research in the area of connectivity in vehicles between each other with roadside infrastructure and various types of ways of facilitating connectivity in robust, resilient ways in these very challenging environments. So beamforming, most of you have probably heard of this term. It's a sort of the technique of projecting energy, projecting signal energy in specific directions and not in others in order to maximize signal noise ratio and minimize interference from, and also increasing capacity and a number of other benefits. But bumblebees, how the heck do bumblebees factor into connected vehicles? Well, in this talk, I'm going to be sort of giving a perspective on the work that I'm doing that actually combines both of these two worlds together, okay, under the umbrella of connected vehicles. Okay. So first of all, before I continue, I want to acknowledge several sponsors of this research. Okay, this research actually has been conducted since 2009. So I've been working in connected vehicle research since I've started my academic life after my PhD studies. But in particular, things really picked up in 2009 when Toyota Infotechnology Center USA started sponsoring me to do some work with respect to connected vehicles, and especially connected vehicles in environments when there's not enough spectral bandwidth to accommodate all wireless communications between vehicles. And I'll explain a little bit about that later in this presentation. I would also like to acknowledge the generous support from the U.S. National Science Foundation through several grants, which has helped facilitate a lot of this work, especially 1547-291, which has been sort of the prime funding source for the Bumblebee connected vehicle research. Lastly, if you use MATLAB, you'll know that the company MathWorks is behind the implementation and distribution of that software. And they've been very generous sponsors of this research over the past several years as well. So the presentation, I'll first describe a little bit about what my research lab does. What is WiLab? What's the Wireless Innovation Lab? I'll then do a little bit of motivation. Why do we care about vehicles talking with each other? Why do we care about connected vehicles? What is such a big deal about them? And then I'm going to be talking about the big concern, which is, okay, so suppose that vehicles should be connected for whatever reason, right? Do we have enough spectral bandwidth in order to support all the vehicles we want to be connected on the roads? And then talk about this concept called Vehicle Dynamic Spectrum Access, or VDSA. I'll then go into the concept of the Bumblebee. And very specifically, there's one behavior of the Bumblebee that we'll be leveraging in order to support connected vehicles, which is called Bumblebee foraging. Just like you would forage for food, or deer or other animals would forage for whatever they need in order to survive, bumblebees also forage. They forage for nectar from flowers. Well, that behavior can be very useful if you're trying to now forage for wireless spectrum to communicate across. I'll then talk about vehicle beamforming, and then finally focus on a use case, which is called vehicular platooning. Okay, so first my lab. So this is a little bit of a pixelated picture, but I wanted to make sure again that bandwidth-wise, this would actually communicate over the air. So the Wireless Innovation Lab is about people. We're all very interested in all aspects of wireless communications. And in particular, we not only do in my research lab, we not only do fundamental research, but we also look at how do we do applied research. How do we bridge the gap between the theoretical concepts and sort of the practical applications? So we're both fundamental researchers and experimentalists. So it's really a team effort amongst us all. So at Worcester Polytechnic Institute, at WPI, my lab, we're really close, we're really active, we're really keen on looking at solving problems, both theoretical and applied, in wireless communications. So our mission, what we try and do is we try and educate and mentor the next generation of leaders and innovators in wireless. We try and do fundamental and applied research and build proof of concepts. And we also try and find solutions to technically challenging problems that are relevant to today. And we do quite a few things, but our core competencies are in 5G communications and networking, satellite and space communications, machine learning and cognitive radio, connected and autonomous vehicles. So this presentation's a lot on the connected and autonomous vehicle side, and software-defined radio prototyping. As for myself, I think I mentioned this enough. I'm a professor in electrical engineering robotics. I have 8 PhD students and 4 master students. William was very kind to mention that I was the past president of the IEEE Vehicular Technology Society. And I'm also involved in several other activities, both regional and national. And I've published about 50 journal papers, 95 conference papers, 9 book chapters, and 3 books, including the one you see here, which is actually free. You can download this free electronically, and it teaches you how to do digital communications using software-defined radio. Okay, so on to the fun stuff. So connectivity, vehicular connectivity. So if any of you read Wired or any other sort of high-tech journal or magazine or YouTube channel and such, or watch the news, you always hear about self-driving cars. You hear about how wonderful they are, how we're after over the last several years, what seemed to have been science fiction, which actually self-driving car technology has been explored for about 70 or 80 years. It's actually been decades that self-driving cars have been explored. But the last 4 to 5 years, we're beginning to see self-driving cars becoming a viable road vehicle that we can see on highways and streets in the next couple of years. So, like for instance, one of the main prime movers, if you will, of self-driving car technology is Google. As we see here, this little cute little vehicle has a LiDAR on top, this little black thing, and which is really neat. Probably has radar and vision systems, and it drives on its own. This is probably done in Silicon Valley in California. And everyone talks about how wonderful, how this technology is evolving, and there's like a lot of advancement, and it's all great, right? And one of the main reasons behind why self-driving car technology is taking off. So one, obviously, is the computing technology is at such a level that it can process all the situational awareness information around that vehicle to quickly make decisions on how the car should act and behave. Now, I mentioned something really important in that sentence I just mentioned, which is situational awareness. So situational awareness is sensing technology. It's gathering information around the vehicle. Where am I? Who's around me? What are the conditions? And what should I look out for? And then that gets fed into an algorithm, could be AI, artificial intelligence, or machine learning, to process that situational awareness information to then say, I need to do XYZ in order to drive safely. Now, what we see here is like a number of modalities in terms of how a vehicle senses around it. Everything from like the blind spot detection, which is already available in a lot of cars and trucks and such. Parking assist, like, cars who can park themselves, adaptive cruise control. And this is all facilitated by technologies such as LiDAR, long-range radar cameras, ultrasonic sensors, and the like. So this is an image, okay, of what LiDAR sees around a vehicle, right? So that funny little thing that I pointed out, a couple of, like this little black thing here, most likely if like, it's like one of those $70,000 or $80,000 US LiDAR units, it produces this thing called a point cloud, which is essentially the LiDAR emits a laser around the vicinity, and then the reflections come back to the LiDAR unit. And based on like, the duration of how far it's taken that laser beam to hit and then reflect back, you can actually discern where's the walls, where's the light posts, where are the people, everything around that vehicle, which is great. Okay, fantastic. That's great sensing technology. And why do we do self-driving? Again, like, other than the fact that it looks cool, right? And there's a lot of like really interesting conveniences around it. Like suppose you have a disability, suppose you can't see, or you are impaired somehow in your ability to drive a regular vehicle. Self-driving cars give you the ability to get back on the road, give you that great mobility to go from point A to point B. Right? But the prime mover, what a lot of people have been looking at self-driving car technology for, is the fact that it takes human error out of the equation when it comes to car accidents and to car fatalities. So the idea is, when you look at these curves, okay, what we're looking at in particular is this thing here on the right side, the total deaths, right? And what we're looking at, okay, over the years, right, is this thing of like, deaths per billion. Like this data is like it talks about, like, just in the United States alone, what it shows is that we approximately have about 35 to 40,000 deaths per year on American roads, and a lot of those are due to human error, right? So what happens if instead of human error, where somebody made a bad judgment call and says, I'm going to run that red light because I think I can make it, and then suddenly gets into a car accident and people die. Self-driving car will stick by the rules of the road. It will have really good situational awareness, And it'll take that sort of those poor judgment calls at those rare instances out of the equation and potentially reduce the total deaths in the United States by due to vehicle collisions and such. So there's an issue though with these sensors that like everybody's been hyper focused on. Like, so I'm building up to the big punchline here. So folks, bear with me. There's a reason. There is like, I'm looking at this over the past several years. I'm looking at these self-driving car platforms. And everybody talks about how great the LiDAR is, which is this is a tiny little cheap version, okay, to the right image here. People talk about radar. This is actually my hand. I'm actually holding a demo version of an automotive radar that you would have like in the bumper or something like that. So this thing on the left side, right? And then in the middle, people talk about vision technologies, right? Like image processing, video technologies, and then it somehow discriminates objects in front of you from open space. The problem with all of these technologies is that they're all line of sight. What happens after that first car? Can you see it behind it? What about two cars? What about buildings at intersections? What happens if your field of vision is impaired or these sensors' fields of vision are impaired? You lose situational awareness, right? So like the premise, okay, for the connected vehicle technology is that we're going to reach a plateau in terms of situational awareness where these self-driving cars are going to operate. And so there's going to be not comprehensive situational awareness. They're like the self-driving cars are going to be making decisions based on whatever information they have, and it might not just be enough, right? So that's where wireless connectivity comes in. Because the fact of the matter is that wireless, depending on what frequencies, of course, is not dependent on line of sight if the frequency is low enough. So, oh, there's a building? Well, at this frequency, the wireless signal can just go through the building or it could diffract around the building, but it's not a problem. I don't need line of sight for that in order for my signal to go from point A to point B, or my vehicle to communicate and find out what other vehicles are doing around me. So wireless connectivity is the game changer for the a self-driving car market, especially for a self-driving car market. And only now are automotive manufacturers or manufacturers of self-driving car platforms beginning to see that. Okay, so this is a good time to be in the connected vehicle world and collaborate with folks in the autonomous vehicle world. Okay, so this is exactly a case that I'm trying to advocate. Let's say this tiled roof building over here, and the red car doesn't necessarily see this car at the corner until it's too late. Let's say if this car is going 50 kilometers per hour, that car is going into that intersection. Bad things happen. Like bad things as in that car, it will be too late for, like, you know, the physics of the vehicle, depending on its weight, depending on the conditions of the road, might not be able to brake in time in order to avoid a collision with that other vehicle. Now, the big issue here is the availability of gaining access to wireless spectrum. You might say, oh, okay, no problem. I'm just going to use either 2.4 gigahertz, right, to 2.5 gigahertz, the ISM band, industry, scientific, and medical band, right? It's an unlicensed band. Or I could use the 5 gigahertz band, which is also unlicensed in the United States. Okay, so caveat: a lot of these frequency bands I'm mentioning are have very specific regulatory specifications in the United States. It might be different in other countries, but in the United States, 2.4 to 2.5 gigahertz is unlicensed. The 5 gigahertz band, which goes up all the way to 5.8, 5.9 gigahertz, that is also unlicensed. And then there's 75 megahertz of spectrum right after that, that is licensed and is the only licensed frequency band for vehicle communications, right? So 75 megahertz of spectrum in the United States is all that is there that would allow for vehicle communications to occur. And then everything else is unlicensed spectrum. So it's dog eat dog. So you're going to have to compete with 5G communications. You're going to have to compete with Wi-Fi 6. You're going to have to compete with every other wireless communication system out there that's using that unlicensed spectrum. So a couple of developments very interesting developments. The 6 gigahertz band, which goes up all the way to 7.125 gigahertz, right? As of a couple of months ago, the FCC, the Federal Communications Commission of the United States, just made that unlicensed access. So, hey, great. That's potentially more unlicensed access for vehicle communications. Bad news, that 75 megahertz of spectrum, the FCC just issued a notice of proposed rulemaking that they're going to cut that in half. So if you think 75 megahertz of wireless spectrum is not a lot to support vehicle-to-vehicle communications, half of that's even worse. So we have to come up with a way to be able to support vehicle-to-vehicle communications if we want self-driving car technology to really have that comprehensive situational awareness. Okay, so first of all, like, this is kind of a shoddy attempt at showing, like, the potential of how vehicles can really connect with each other. This is like at a more macroscopic level. This is actually a kind of a pixelated version of what the WPI campus is in Worcester, Massachusetts. So WPI is here, and Worcester, this is the northern part of the city of Worcester. And if you want all the vehicles to connect with each other at a macroscopic, not time-sensitive level, you can have something called like vehicular Internet of Things, right? That's great. But let's say you want something that supports time-sensitive operations. Well, then you're going to need bandwidth. You're going to need reliable access to that bandwidth, and you're going to need a lot of it, especially if you have a lot of cars. Okay, and what sort of operations would you need wireless connectivity, self-driving cars, even human-operated vehicles, in order to support safe, reliable vehicle operations? How about the simple lane change? You might say, okay, lane changing, big deal, doesn't sound dramatic. It doesn't sound like something from an action film you see from Hollywood. No, lane changing is actually really dangerous. I'm not sure how many of you drive a car, but imagine you're on a highway, right, or a motorway. You're going 90 kilometers per hour, 100 kilometers per hour, and you want to go into the faster lane, right? Here, the illustration that I have, the cars are traveling from left to right, and the passing lane is the top lane. So this is the American version of a motorway. Like, of course, New Zealand and a lot of other countries, it's the opposite. But here, like, this assumes an American model. It's quite frightening if you're trying to do a lane change. You're traveling at 80 kilometers per hour in sort of the regular travel lane, and then traffic is passing you at 100 kilometers per hour, and you want to pass car 2 and you're car 1, but car 3 is approaching really quickly, and car 4 is right in front of you in the passing lane. So there's like, and imagine car 1's autonomous, car 1's self-driving. It's going to require a lot of information. How can this be done safely? Okay, just based off of LiDAR and radar and all these other things? Well, maybe it's possible, but this is a prime example where you could use connectivity in order to support an operation that seems benign, but it's actually quite complicated, the lane change. Even car following, which I'll talk about in the use case, especially multiple cars following, is quite complex. It's quite complex, especially when no humans are involved, right? So that's why that, as well as the other model, the V to I, the vehicle to infrastructure model, is quite important in terms of connecting all these vehicles. This is actually what I'm going to be talking about at the end of this presentation, which is called platooning. So platooning is when you have 1, 2, 3, 4, 5. It could be N cars. They're all traveling in a lane together, in unison, and they're all coordinating their actions together, right? So they're going to need connectivity with each other in order to exchange what they're going to be doing, as well as potentially with the surrounding environment, right? So this begs the question, like, is there enough wireless spectrum? And my answer would be, is another question. What is enough? Well, this is what a typical, well, I would not say it's a typical American highway. This is actually a really bad, like really bad case, but I've been at highways around the Boston area, right? This is where Worcester's located close to Boston. But there are a lot of highways out there that look very eerily similar to this. And imagine in just a short stretch of road, you're going to have connectivity and enough wireless spectrum to exchange information and situational awareness to be gathered by all vehicles, all other vehicles around their environments in a mess like this. Is there enough wireless spectrum? So what I'm going to be talking about is this idea of, first of all, finding out, do we have enough wireless spectrum? What's the behavior of that wireless spectrum? And then how do we take advantage of what we call spectral white spaces, empty portions of spectrum, in order to fill those empty portions with communications that we could use to support traffic scenarios such as this, such that every vehicle, human operated and self-driving, okay, with enough situational awareness information to avoid potentially any collisions and make the road safe. Okay, so a scenario like that already motivated the fact that in terms of dedicated wireless spectrum, we're already a little bit in trouble here in the United States, because 75 megahertz now divided by 2 is all we got across this entire country dedicated to vehicle communications. So we got to come up with ways of trying to access wireless spectrum in more opportunistic approaches in order to facilitate communications when we have hundreds of cars across 1 kilometer of road. So the idea, the vehicular dynamic spectrum access concept, is as follows. Suppose we go into spectrum where we are not the licensed user, we're not the licensed application. Suppose we go into unlicensed wireless spectrum, like 5 to 5.8 something something, or 5.9 to 7.1 gigahertz. We're not the licensed application in either of those bands. So we're going to have to fight with all the other wireless applications operating there. So what vehicular dynamic spectrum access does, it's an opportunistic approach where, suppose in this case we have the assumption of primary transmissions, but in an unlicensed band, there's no such thing as primary, right? If, let's say, on the other hand, folks have looking at digital television wireless spectrum as ways of like, because television spectrum is not fully utilized in the United States, so the white space, the empty spectrum there, potentially could be used opportunistically to be used by vehicle communications in order to support vehicle-to-vehicle comms, like between A and B, or A and D, or D and C. So as long as we don't interfere with the primary transmissions, so if it's digital television, that would be the gray blocks here on top, and the red and blue and green would be our vehicle communications that would fit in between and not interfere with any of those primary transmissions. In unlicensed spectrum, right, like the 5 gigahertz band and the 6 gigahertz band, these would instead be, instead of primary transmissions, maybe other unlicensed transmissions that got there first. And our communications would wrap around those and not interfere with them. We would coexist with them, but still support vehicle connectivity. And with that vehicle connectivity and that information exchange, we can then do onboard decision making, such as how do we change lanes, how do we follow that vehicle, how do we do platooning, and all those other very complicated maneuvers, right? So what we would do is we need a way of doing vehicular dynamic spectrum access such that A and B can talk with each other, maybe in this red part of the spectrum here, in this red part of the spectrum here. This x-axis here is the frequency. And A and D can communicate in this blue band, and D and C can communicate in that green band, right? So what we did, the first step, is understanding what the spectrum landscape looks like. So what I did in 2009 with Toyota is, okay, let's look at, before we had all this massive amount of unlicensed spectrum, We had digital television in the United States, which was beautiful spectrum from 460 megahertz all the way to nearly 800 megahertz. We had a few television channels, and the rest was empty television white space. It was just spectral white space everywhere. And what do you know about television? Well, television never goes off the air. It's 6 megahertz wide, it's always on, and it's very predictable. So it's like, oh my God, this is such beautiful spectrum. But here's the problem. Cars move. And wireless spectrum doesn't look the same from one point on a highway compared to another. So what we did is we did an empirical measurement study in 2009 where we physically took wireless spectrum measurements of television across all 139 miles. That's a little over 200 kilometers of highway in Massachusetts. Every 10 kilometers or 5 kilometers or so, to kind of see, okay, what does the wireless spectrum at the television band look like at this point, at this point, at this point, at this point. So like, for instance, this diagram here in Boston, okay, like suppose this is a 6 megahertz television band, this is a 6 megahertz television band, this is 6 megahertz television band. And in each one of these is a 6 megahertz television band. Oh, digital television is beautiful because you could right away tell it's television because it's rectangular in shape. It has a pilot tone to one side. It sticks out. It's absolutely beautiful. And some are occupied. That's the gray boxes here. And some channels, 6 megahertz channels, are free. That's where we would do the opportunistic spectrum access, the VDSA. But notice how in Boston, we have some empty bands and others are not. In Auburn, Massachusetts, which is about a third of a way across the state of Massachusetts, we have a different allocation of available versus unavailable. Springfield, Massachusetts is midway across the state. Lee, Massachusetts is nearly at the other end, the western end of the state, and we have even more spectrum available. So understanding your spectrum, especially as a function of distance, is very important. So that's exactly what we did here. Here's a map of Massachusetts. So Boston is here. New York State is here at the left. And each one of these blue pins represents where we did a measurement to see what is the availability of wireless spectrum. And this heat map here, okay, tells us, okay, so it's Interstate 90. That's the major highway that goes east-west across Massachusetts. So what this heat map tells us, okay, is the availability of wireless spectrum in Massachusetts, where we can and where we cannot transmit across Massachusetts. So the x-axis is frequency, so 470 megahertz all the way to 800 megahertz. So that's the digital frequency band in the United States. Again, this might be different depending on which country you're located in. The y-axis is distance. Boston, Newton, Framingham, Westboro, Auburn, Sturbridge, Palmer, Chicopee, Blanchford, West Beckett, Lee, West Stockbridge. So those are towns and cities, all along going from east, which is Boston, all the way to west, West Stockbridge, which is on the border of New York State. And what the heat map tells us, okay, is the threshold. What's the maximum power in dB that I can transmit in each one of those? So you might wonder what are these perfectly narrow rectangles? Those are precisely 6 megahertz wide. So each one of these narrow rectangles are 6 megahertz wide. And so each of these is a digital television frequency. And the deep blue, minus 60 dB, that's the maximum limit of transmit power that I can transmit my wireless signal in that band, okay, and not interfere with a digital television signal. And then red, bright red, is 0 dB. So the bright red is ideally where I would want to transmit, mainly because that's the maximum power I can pump out, and I would have the best SNR in those scenarios, depending on the distance between vehicles. And blue would be like I'm maximally constrained because I would potentially be interfering with a television transmission. Okay. So what I've done is here's a few publications from that research from Toyota. This was like a 3 or 4 year long research collaboration with Toyota. So we publish in a number of venues, including IEEE Communications Magazine. We publish in a few conferences, including VTC, that's the VTS's flagship conference, and a few other places. Okay. So that's the first part. So what I've just described, okay, I've set the context saying that spectrum as a function, wireless spectrum in a vehicle sense there is an element of time, but it's also very heavily dependent on distance along a roadway, right? Now, and that we have to be very careful if we're going to opportunistically take advantage of unused spectrum, that we're always aware of what that situation looks like down the road, because otherwise what will end up happening is that we might interfere with another signal, primary, or another unlicensed secondary signal unintentionally, but still, doesn't matter if it's intentional or unintentional. Okay. So I think there was a couple of questions, so I'm going to try and bring that up. Actually, what I'll do is I'm going to answer questions at the end, because it seems I will answer them, but I'm going to answer them at the end in order to keep my train of thought going. But I just scanned through what the chat, and they look impressive, so I'll definitely answer them. Bumblebee foraging. So what the heck is bumblebee foraging? How does that get involved in all of this? Okay, so funny story. So one of my research interests is cognitive radio, right? So you hear the word cognitive. Now, cognitive sounds like brain, sounds like some sort of intelligence, right? And I don't know, a lot of folks were like saying, oh, cognitive radio, and somehow the knee-jerk reaction, people instinctively say, human cognition. But what ended up happening was I had a very interesting conversation with my grad students one day, and was like, well, why do we have to have such a complex cognition process? Why not something a little bit simpler? Why not something like an insect or some simpler animal? So at that same time, a press release came out. This is how biologists look at bumblebee behavior, okay, and how they act. These things, these funny looking color things, these are plastic flowers. And the colors, they put different levels of nectar, and what they do is they observe bumblebees. They like release bumblebees into this screen room, and they look at how the bumblebees observe, act, and behave, and remember the color of flowers in order to memorize which flowers have a lot of reward, a lot of nectar, and which ones do not. Very interesting. Why not apply this to how to act with respect to gaining access to wireless spectrum? These frequency bands are very rewarding. These frequency bands are awful. They're not rewarding at all, very poor SNR, can never really do anything with them, constantly being interfered with. Can we use the bumblebee behavioral model as the premise for accessing wireless spectrum in a VDSA context? That would be awesome. And so we actually came up with something. So we have an IEEE Access journal paper. So it's open access, so everyone can access it, with colleagues of mine from the biology department here at WPI, whose expertise are in bumblebee behavior. And so what we did is we tried to bridge the gap between the biology world and the electrical and computer engineering world, which is no small feat. Even the word sampling in an electrical and computer engineering world actually means a completely different thing in the biology world. So it took about a month for us to figure out that one. But let's zero in, okay? Let's see how bumblebees behave, okay? So bumblebees, the way they behave is step one. What bumblebees do is they actually go around and they sample all flowers, they memorize color, and they try and determine reward. Okay, so and just a heads up, bumblebees are very different than honeybees and ants, because you've heard of like swarm optimization and ant colonies and honeybees and all that. The thing is, honeybees and ants are socially dependent animals. Bumblebees are socially independent animals. They'll take in all the information, but then they're going to act independently. So they don't necessarily go according to whatever the hive or the colony says. So what they'll do is they'll say, oh, very interesting. Purple flowers have the most reward. I'm going to be sampling purple flowers. But once in a while, they're going to sample a yellow flower, red flower, white flower. So they'll go to the flower. In this case, it's the white flower that has the most reward, and just keep on sampling white flowers. But occasionally, they're going to like check out other flowers. And what they're also going to do is they're going to see where rewards increase and decrease. And they're going to, at some point, they'll say, oh, red flowers are now very rewarding. I'm going to go after red flowers. Okay, no longer white flowers. How does that mirror to a vehicle context with VDSA? Well, what happens is here in a vehicle context, suppose you have channels 1 through 8, okay, that your vehicles can access. 1, 2, 4, and 8 are constantly being used. There might be some intermissions where they're unused, but for the most part, they're not very desirable. So 3, 5, 6, and 7 are actually quite attractive to take advantage of. So I'm opportunistically speaking, I'm going to take advantage of 6 because it's the farthest away from a used channel. So that means I'm going to get the least amount of interference that's coming out of band from any used channel. So I'm going to take advantage of that. Then over time and across the road, the environment changes and some channels become more occupied, some are going to become less occupied. And then all of a sudden, 6 becomes more occupied by other transmissions. Not very desirable. So what's the next sort of like sampling again the different frequencies, the different channels? What's the next good one? Oh, channel 7. I start transmitting there. So now the key here is, can we translate bumblebee foraging behavior over to vehicle dynamic spectrum access? And the answer is yes. It's actually kind of interesting. Even if you go a step further, not just bumblebees, there is a concept. There's several books written on this in the biology circles called foraging behavior. Wolves do it, moose do it, bumblebees do it, sharks do it. There's very specific behavior that animals follow in order to survive. So why not? The premise is, why don't we build that type of functionality into our radios? Okay, so what we want is basically a radio that it can sense, it can see what the wireless channels are around it, and then find the best suited channel, the one that produces the best possible results for communications, in order for it to communicate information with another vehicle. Now, in addition to that, there is one thing that's really, really super duper important, which will come up later in some of the results, which is I want to minimize the amount of times that I have to switch channels. Because when I switch channels, I take a hit in performance. I've got to sort of resync my channels. There's a lot of overhead. It just becomes kind of a unpleasant situation where I have to sort of pick up my tent, go to another frequency channel, and then reestablish communications with another radio. And I lose cycles, and there might be latency that's introduced. And in that time, maybe there's a potential car accident that's waiting to happen. So some key definitions between bumblebee nomenclature and vehicle nomenclature. So the channel in the vehicle world, the vehicle communications world, is like the floral species. Channel sensing is bumblebee foraging. Radio discovery of new channels is bumblebees discovering flowers of a specific type. And the comparisons go on and on. So coming up with a common lingua franca between biologists and electrical and computer engineering wireless people was very important with respect to this interdisciplinary research. So the algorithm shown here, and this was actually published in VTC in 2018, the spring edition. The way it works is you initialize the model, and the bumblebee discovers the flower type of a specific type. So let's say it's an unoccupied channel. Okay. So, and what it does is several things. So first of all, has that flower type been visited before? Is it a white flower? Is it a red flower? If no, what you do is you say, okay, I need to evaluate how much nectar it has. Is it a really rewarding flower or is it not? Okay. If I have, then I need to update my memory with respect to the amount of nectar that that type of flower has. Now, does the nectar amount exceed the harvesting threshold? So this means like essentially, is it worth my while for me to gather that nectar, or is it is the amount of energy expended to gather that nectar not worth it? Uh, if it's not above that threshold, I go to another flower type. If it is, then I harvest the nectar and then I exit the algorithm, right? So it's very simple, right? And even you could probably model it to human beings as well, right? Is it really worth going to that restaurant across town, or is the restaurant down the street good enough for dinner, right? So this is what I meant by switching costs. So switching costs is the amount of energy, right? The penalty that I take for switching from one channel to another. So I really do want to stick to one flower, to one channel as long as possible. I do not want to restart communications in a completely different frequency band. It's just not worth it. It takes energy, right? And what this figure here is as well from the VTC conference from 2018 was a kind of a nice histogram from the GEM-V2 traffic simulation that we did that kind of showed the switching costs when we had both highway conditions for vehicle-to-vehicle communications and vehicle-to-vehicle communications in an urban environment like New York City or any major big city. And what we noticed is that in a highway condition, switching costs were okay, right? But in a urban scenario, it actually was pretty bad. And part of it is just the nature of the environment. Like cars are in close quarters. It's highly variable. It's highly it's very time varying. There are a lot of vehicles. There's a lot of things going on. Cars come into the network topology. Cars leave the network topology. It's a mess, right? And so being able to find a stable frequency band in order to communicate across, and then having to lose it and find a new band, and then the latency associated with trying to establish a new link or an existing link, but in a new frequency band is quite bad, right? So, and then what we also looked at is when we looked at packet rates, when we send lots of messages. And the probability, this is actually really important, the probability that all channels are busy, right? So, and again, what we looked at here, okay, we modeled this again using the GEM-V computer simulation for like traffic modeling and such. As we increase the packet rate for each vehicle, like so every vehicle that we were modeling in this traffic simulation, obviously what happens is you begin to fill up all available spectrum bands and you begin getting all channel busy scenarios here, especially as we progress in this specific, this is a very, very specific trace, if you will, of a computer simulation with both 10 messages and 20 messages per second for that computer simulation. So this is really bad because if all channels are busy, we're in trouble, because what ends up happening is, suppose I don't have, again, enough dedicated wireless spectrum to do emergency communications, and I'm dependent on this sort of secondary access, this VDSA, and I have no way to communicate across frequency, to communicate to the vehicle surrounding me, saying, hey, there's a car accident or a very dangerous situation up ahead. This is not good news. Then those cars around me don't have complete situational awareness. Right? So over the past couple of months, what we've been doing is we've done some experimentation with IEEE 802.11p. So that's one way. It's a 5-layer representation of doing vehicle-to-vehicle networking, right? And it's an IEEE standard, which is based off of the IEEE 802.11 Wi-Fi standard. So it's almost like Wi-Fi, but there's a few tweaks to it in order to support it doing vehicle-to-vehicle communications. Another wireless standard that has come out is the CV2X, or Cellular Vehicle to Everything standard, which is from 5G, right? So the 3GPP standards, folks. And what we've done, okay, is we implemented both of these using software-defined radio. Again, we do a lot of prototyping in my research lab. So that team you saw at the beginning A lot of those folks in that photograph know how to not only do the theoretical wireless analysis and propose new solutions, but we also know how to build it in software-defined radio. And what we in particular did is we kept everything else the same in terms of the protocol stack. So we use something called Open Air Interface. So it's an open source project that implements 4G and 5G, as well as the enhanced packet core and all this other nice, good networking stuff. But we tweaked the physical layer in order to implement the Bumblebee-based vehicular dynamic spectrum access algorithm that we saw before. And we also had a PC5 sidelink channel that connected the vehicle 1, vehicle 2 to each other in the CV2X model. And so this is the actual representation of that. So we had two X310 USERPs, right? So these are software-defined radios that are used a lot in the community. We had an octoclock. This allowed us to synchronize both USERPs. So we actually didn't put this into actual cars. Let's just say that that's a little bit more expensive. It's doable, and that's probably going to be the next step, especially once quarantining is over here in the United States. So, but in a controlled laboratory context, especially also with respect to frequencies, because we don't have license. This was using licensed frequencies, so we could not do this broadcasting over the air. But what we did is we had this guy here, the GPS DO, this is the disciplined oscillator that's GPS related. So we had an antenna going to the roof. So we were getting the GPS clock. It's connected to the octoclock. That allowed for synchronization of these two radios, and these two radios modeled the vehicle-to-vehicle communications using the CV2X standard, which was implemented using the OAI open source package. Okay, and what we did is, in this case, we were studying, among other things, so instead of computer simulation, this is actual hardware implementation results. We were looking at the impact of memory size. So what do you mean by memory? Well, I want to see how the spectrum looks like, and the experiences I had with the wireless spectrum over not just like the last experience, but like over the last several experiences, maybe a couple of minutes, and see how the spectrum behaves, such that would feed into my Bumblebee foraging behavioral modeling of wireless spectrum access actions to know, oh, that spectrum's always busy, stay away from that. Oh, that spectrum's always available, use that. And we got these performance gains. But there's, of course, a trade-off, right, in terms of like the amount of available channel bandwidth. So the CV2X standard allows for both 5 megahertz channels and 10 megahertz channels between vehicles. So we looked at both of those, and the latency it took with respect to being able to, given these different memory sizes in order to access these wireless channels based on, past memories of how the channel behaved spectrally in terms of its occupancy. Okay. And so these are some of the publications. So the one that the results we just saw was actually just published in VTC May 2020. This was a virtual conference, but nevertheless, the paper should be available, if not already, in IEEE Explorer, but very soon. And there are quite a few other papers. The one that, if anybody's really interested to kind of like dig in and say, what the heck is a Bumblebee behavioral model? Check out the one in IEEE Access. I mentioned this before. IEEE Access, if let's say in the least amount of search terms, look for IEEE Access Memory Matters, Bumblebee. If you put in just that into Google, boom, you should be able to get this, okay? This is kind of like the first paper that describes everything that I just was talking about with respect to Bumblebee behavioral models and the vehicle-to-vehicle communications, all right? Now, it's one thing to access wireless spectrum, but there are other techniques, signal processing techniques that you could use. And I mentioned this before, there's beamforming. So beamforming is the technique of using, in this case, we are using an electronically phased array in order to combine different wireless signals emitting from different antennas in order to constructively and destructively combine to project energy and signal energy in some directions and not in others. So I'm just going to jump ahead in the interest of time. But what we were doing here is this idea of we have a transmit vehicle, we have a receive vehicle, and what beamforming does is the gray represents the electromagnetic energy coming out of a phased array, which is represented by these triangles on top of the vehicles. So energy would be projected, signal energy would be projected primarily to the receive vehicle and minimized elsewhere around the vehicle. And then the receive vehicle will be maximally sensitive to energy coming from the transmit vehicle and not as sensitive to signals coming from around it in other directions. So what we're effectively doing is we're doing spatial filtering. So some math, right? So this is like, you can go to any sort of phase array textbook, but what you do is if you have a bunch of isotropic sources, so let's say dipole antennas, the array factor, okay, tells you, given the number of antenna elements, tells you what like your beam pattern is going to look like, right? So it's going to be maximally sensitive or maximally project electromagnetic energy in one direction while not in others, right? And then you can calculate how much power is going to be received based on that pattern. And then using that, okay, we can then start like, if we like, so that's physics. So there's no probability associated with that. But, okay, so here's the big caveat. There are going to be two issues with respect to beam forming. One, you're only as good as knowing where your intended receiver is. So if your receiving vehicle says, I'm here, but there's GPS error involved, well, it's going to be a problem because you're going to be projecting like this guy here in the figure 16 towards where the vehicle says it is, but the vehicle is actually located here where the black triangle is. So that's a problem, right? So GPS error, which is a random phenomenon, is actually well studied. So what we did is we actually looked at positioning error calculations, right? So we looked at things like dilution of precision based for GPS position measurements, and then also user equivalent range error, so DOP and URI. And what we did is we were able to come up with statistical models that we were able to factor into the performance calculations of when we do beamforming between two vehicles where they're both beamforming to each other. And what we did is we both evaluated the signal to noise ratio when we increased and decreased the distance between transmitting and receive vehicles. And we get this nice pattern as we increase the number of antenna elements on each of the vehicles, right? And okay, so what happens when you increase the number of isotropic antenna elements in a phased array? Well, what happens is your beam pattern becomes much more crisp. It becomes much more precise. It becomes the bore site becomes the beam pattern becomes more narrow. So it's less likely it's going to spew energy all over the place. Now, what happens is the energy gets projected in a specific way and nowhere else, which is great. So what we have here, right, is what we're looking at is the signal to noise ratio, and when this is I forgot, this is in meters. Yeah, it's in meters. So minus 500 meters is when the transmitting vehicle is 500 meters behind the receive vehicle, and 500 meters here is when the transmit vehicle is 500 meters ahead of the receive vehicle. Phased arrays, what they do with the beam patterns is that they can electronically steer it, which means I can just continuously have these two guys point at each other continuously. The maximum signal to noise ratio is when there's zero distance of separation between the two, and we get like really nice, awesome signal noise ratio in dB. This translates into when we have bit error rate, okay? As we increase the antenna elements, what ends up happening is, as of course, when you get farther and farther away, your bit error rate becomes worse and worse, but you still get better performance when you have more antenna elements because of like how it minimizes, let's say, it projects energy much more in one direction than any other direction, and it minimizes also the very important second issue, which is interference, and especially interference from other vehicles who might also be beam forming and driving by you. right? So we looked at that, and this actually got published in VTC 2020 spring, also in Antwerp, but it's a virtual conference, so it should come out soon. So in addition to GPS error, we looked at interference from other vehicles, which is very possible, especially those that don't even connect with your network for more than a fraction of a second. So what we looked at, again, is the impact of moving vehicles and the interference on a pair that are communicating with each other, and that pair is 250 meters apart. And what we see here, you might say, okay, what's that hump? Why is bit error rate getting really bad? It's because the vehicle that's interfering is now in between the two vehicles. As the interfering vehicle is very far away, either 0 meters away, or when interfering vehicle is far away from the two other vehicles that are 250 meters apart, its interference does not have too much of an impact, right? 10 to the minus 4. Well, it's kind of an impact, but it's not as bad as if it's right there, just continuously transmitting at accidentally the receiver, right? So that paper with the interference, this is the one. Navitha Kanthasamy is a PhD student that's working on it. And I'm collaborating with a professor from aerospace engineering, Raghu Kalagi, who does a lot of control theory. So we did a lot of control theory in terms of the tracking the beam pattern with respect to the vehicles and stuff, in order to have that lock. And he's also an expert in GPS. So he was able to help a lot. And then the positioning errors was Navitha's first paper, and that was from 2018. So last but not least is the use case. So we hear in the United States, there's a lot of talk about, like, what's the killer app? What's the first app about self-driving cars on the road? The big one, the really big one, okay, so obviously, if you want to buy a really expensive luxury car and self-driving, you can have at it. You can buy that. But the first commercial application will probably be autonomous trucking. And there's a lot to be said about trucks operating in platoons, because when they're operating in platoons, what they do is, if you operate in platoons, the first truck is going to experience a lot of aerodynamic kind of like resistance, because here's this like 12 to 15 foot tall truck that's trying to move all this air. But if the other trucks are close behind it, it falls into a slipstream and it meets very little air resistance, and therefore is fuel efficient. So you get a situation that kind of looks like this. So you have platoon 1, car, or truck, and then platoon 2, truck. So how do they coordinate with each other? They will connect. And the big worry, and this was a paper that we published also in VTC 2020 spring in Antwerp, is what happens if you have collaborative adaptive cruise control, or CACC, and connectivity, and you're using digital television spectrum, and oh, by the way, you have groups of digital television the digital terrestrial televisions that are also nearby that could potentially be interfered with. What do? Well, you use Bumblebee foraging. So this is actually a collaborative project with some really good friends of mine at Poznan University of Technology in Poznan, Poland. And what we did is we looked at the spectral white space behavior. Okay, so these are actual measurements and then approximations of spectral channels, okay, at 490 megahertz and at 522 megahertz. And what happens is this purple line here says that's the threshold for receptions. Like, below it, it's like too weak for a DTT to pick up the signal, but above it, it can very clearly pick it up. Can we use the Bumblebee algorithm for opportunistically accessing wireless spectrum here? So when, let's say, for instance, this green line goes below the purple line, can we take advantage of that wireless spectrum at 522 megahertz, even for a moment, to communicate some vehicle-to-vehicle communications? And then here, the black signal, the black measurement here, like the 490 megahertz, it's almost all the time below the purple threshold, except for here and here. That's a very nice spectrum, because I could use those moments to communicate information, okay, on this stretch of road, and not interfere with anybody listening to that TV channel. So what we did is we looked at successful packet reception rate. And we looked at, like, the control channel with TV white space with no switching, control channel TV white space with Bumblebee, and zero costs associated with the switch. And then we looked at different costs and stuff. And what we got were these trends. And what we were looking at was a platoon where we had the car in position 1, 2, 3, 4, 5. So we had 9 cars in a row. And they were basically relaying to each other, V to V to V to V to V, exchanging information, and trying to also avoid switching as much as possible in that environment, which I showed here. So across 5 kilometers of roadway, the 490 megahertz channel was quite attractive, while the green channel, for the most part, was very, very busy and we could not really interfere with. And so we were looking at trends. And what happened is, when we were looking at this, the probability of successful reception compared to just having a control channel versus control channel with, in addition to that, TV white space, using the Bumblebee, VDSA algorithm with a 6 dB cost, performed the best in all the scenarios where just having a control channel saying you can use this channel, you can use that channel. So like no insight on memory, no sort of like, sort of feeling out and trying to kind of assign rewards on the different channels that I could use and such. We found that the Bumblebee algorithm with that 6 dB cost yielded best results. So, okay, so enough of me and yabbering. So this paper just again got published, and it was at the VTC conference in May 2020. So Pavel Shroka and Krzyszewicz and Sibus and Klix, my PhD student Kuldeep Gill and myself published this. So with that, I just want to thank all of you again for your time and attention. What I'm going to do, this is my contact, my email address. It's alexw@wpi.edu. And what I'll do is I'm going to do a combination of answering. First, I'm going to try and answer the questions in the in the chat, because and again, thanks to everyone for your patience with that. It's very difficult for me to multitask, so I just wanted to present, and then I'm going to address, and then I'll also take questions from the floor. I'll also stop recording this so folks can ask questions more freely as well. So with that, again, thank you for your time, and what I'll do is I will stop recording. So thank you again.